once around the Magellanic Clouds. And you can see the Magellanic Clouds in this fantastic photograph. We have the observatory building of the VLT in Chile over on the right, the arc of the Milky Way low on the horizon in the center with all the dirty dust lanes and 10,000 stars above. But over to the left-hand side, there are two fuzzy patches in the sky, and these are the large and small Magellanic Clouds. Now, these are members of our local group of galaxies. Our local group comprises the Andromeda Galaxy, shown at the bottom, the Milky Way at the top, and the Triangulum Galaxy at the right there, the smaller member of the three. And there are about 30 members altogether, covering a zone that's about 3 million light years in diameter. So I have these main three galaxies and then a number of dwarf galaxies that are in orbit around the individual ones or just floating around in the group. You can see that the Andromeda Galaxy has a couple of little dwarf galaxies associated with it there. We, in the Milky Way, have our own little family of them, and this diagram shows a map of the Milky Way with the large and small Magellanic Clouds, and then we have the Carina, Fornax, Sculptor, Sextans, Bootes, Ursa Major 1, Ursa Minor, Ursa Major 2, and Draco dwarf galaxies, and quite close to the Milky Way there, the Sagittarius dwarf, which was only relatively recently discovered. So the large and the small Magellanic Clouds are perhaps the largest and well-known ones of this collection, and here they are. We have the two images here on the right-hand side, the small Magellanic Cloud at the top there, and the large Magellanic Cloud at the bottom, the SMC and the LMC, as we often call them. And they are irregular galaxies, although there's some evidence to show that the LMC at the bottom there might once have been formed with a spiral structure and a bar across the middle. You can just see a hint of that in the image. Here they are again, a lovely picture of the two of them separated against the background of stars there. And these have both been known from ancient times. They're very easy to see. I've seen them from the outdoors in New Zealand, and it's quite stunning to think just how far away they are. So when you look at them, they look like chunks of the Milky Way that have become separated from it, but they are actually more distant than that, quite significantly so. The large Magellanic Cloud, that's at 179,000 light years. So the Milky Way has a diameter of about 100,000, but is only about 5,000 or 6,000 light years thick. So this is a significant distance further out than the edge of the Milky Way. It's the fourth largest, in fact, of all of those 30 members of the local group, and about a tenth of the mass of the Milky Way galaxy overall. So quite a significant little galaxy. As I said, it probably had a bar structure across a spiral, which you can just see the echoes of today, but it came too close to the Milky Way and got stripped of a lot of its outer layers and rather distorted by the effects of gravity. Now, buried within it and around it, we have lots of interesting objects. This is NGC, the New General Catalogue, a list of objects created by John Herschel, son of William. And so in 1835, he found this one, and this is the largest of about 60 of these globular clusters that are associated with and in orbit round the outer reaches of the LMC. Curiously, the age of this appears from studying the stars within it and the degree to which the most massive ones have evolved. You get an age of about 1.7 billion years, which is much, much younger than the Milky Way or the large Magellanic Cloud. Those are about 13 billion years old. They're very ancient galaxies indeed. So this globular cluster seems to not match at all well. And it has about 100,000 solar masses of materials in it, comprising all those lovely stars that you see in the picture there. It's quite a stunning picture. Also in the LMC is the Tarantula Nebula. And this is a fantastic image of the Tarantula Nebula on the right-hand side. It's inside the LMC, only about 160,000 light years from us, so a little bit nearer than some parts of the Large Magellanic Cloud. And what you can see is a star-forming region where all that gas and dust has been collapsing and it's getting squeezed together by gravity and forming new stars. And what we have is a new star cluster in the center. All those bright white stars clustered together in the middle were formed out of the gas and dust. And now the energy from these stars is blowing outwards and pushing away all the remaining gas in a giant bubble in 3D. I think you can imagine that just by looking at the photograph. So there's about just under 500,000 solar masses of stars being formed in that enormous burst of star formation there. Also buried inside the Tarantula Nebula is this guy, VFTS 243. It's a black hole. It's an X-ray quiet black hole, in fact, and it's probably around 9 times the mass of the Sun, and it's in orbit around a larger companion, a 25 solar mass blue giant star. So in fact, the image that you're seeing is, of course, the blue giant star, and we can't see the black hole. It's black, it doesn't let out any light, and it's quiet at the moment. It's not in the process of feeding. So it was probably a larger mass star, more than 25 solar masses, ran through its life cycle very rapidly and blew up as a supernova plenty of years ago, whilst in orbit around its companion, this star that we can see, the blue giant. And that won't be very long before that blows up and probably either collapses to a neutron star or maybe even to a black hole itself. 25 solar masses is well large enough to probably collapse to a black hole. Now, we have seen other events like this occur in the Large Magellanic Cloud. In 1987, a supernova went off there, supernova 1987A, very famous indeed. In fact, this was the closest supernova that we had seen since modern times, when we had modern instrumentation. And that's still quite a long way away, 160, 170,000 light years. But it was extremely interesting to be able to monitor it with all of the array of modern tools. So 1987A was discovered on the 24th of the month in observatories in Chile and New Zealand in February of that year, and got brighter and peaked in its brightness about 3 months later as the size of the shock wave coming out expanded. When you have a larger disk, even if it's cooling, the larger size means more radiation overall is emitted, even though it's less bright for every square meter. There are just so many more square meters. They get brighter for a while until they start cooling off. And then the light curve shown at the top right there declines downwards. Now, we think this was a giant star undergoing a type 2 supernova, a core collapse supernova, where it came to the end of its life and could no longer sustain itself against the force of gravity because it had run out of options in terms of fusing material together. And the first signal to be received from it was not the light. It was actually the day before, on the 23rd of February, and that was a burst of neutrinos, these ghostly particles that don't interact with normal matter apart from with gravity and the weak nuclear force, could get out of the center of the exploding supernova incredibly easily, whereas the light takes a while to develop and to get itself to the surface and to be able to be emitted and travel. So it's fairly common for the neutrinos to get here first from the very start of the event. And that arrival of those neutrinos tells us that this was probably the result of the core collapse. Now, we have managed to locate now the Progenitor star, the star that blew in previous photographs and catalogues, and it goes by the designation SK-69202. These catalogue numbers are impossible to remember. But it was, before it exploded, a blue supergiant 20 times the mass of the sun with a temperature of 16,000 Kelvin. So very hot indeed on the surface, very massive, very short-lived star that would have lived about 10 million years, something like that, and then detonated as a supernova. But it was a bit of a surprise at the time, because back then received wisdom and theory suggested that the stars that blew up were red giants and red supergiants, not a direct explosion of a blue supergiant. They were thought to have to become red in color, cooling their outer layers before detonation. So it was a bit of a shock, but now theory has caught up with observations, and we entirely think we understand how blue supergiants detonate under these circumstances. And you can see the lovely explosion in the center of the main image there, and a slightly enlarged version at the top right. You can see the shock waves, the rings moving away. And supernovae are like this. The stars tend to be rotating quite rapidly, and that spin creates an asymmetry. And so the explosions tend to find that it's less distance to reach the surface and blast outwards through the polar regions rather than at the equator. And so you get a north and a south bursting of the star out from the north and south rotational poles before the disruption of the equator. So that's why we see this amazing structure. But there remains a mystery, because with a 20 solar mass star detonating and all of that burst of neutrinos, the neutrinos confirm that this was the creation of a lot of neutrons in the center, the electrons and protons being rammed together, positive and negative cancelling out to neutral neutrons, and we would expect a neutron star to be the result of this. But we can't find it. We cannot detect the neutron star. Now, it might be for a number of explanations, one of which could be that it's obscured by dust and we're just not able to see it. But it's also possible that the collapse formed a neutron star and then more material fell back onto the neutron star, pushing it over the 2.2 solar mass Tolman-Oppenheimer-Volkov limit and causing it to collapse down to a black hole. Or it could have formed a black hole directly, because 20 solar masses is pretty big and it's getting towards the point where that might be able to happen. But the intriguing possibility is that it could have formed a quark star. This is an intermediate object between a neutron star and a black hole, and it's a serious contender for what might have happened here with a 20 solar mass blue giant collapsing downwards and crushing the the protons and electrons to form neutrons, but then ripping the neutrons apart to their constituent quarks. And if you want to hear more about that, I have a video called Quark Stars and Strange Matter, and I recommend that one. It's been very, very popular. So that was Supernova 1987A in the Large Magellanic Cloud. Other things in the cloud? Well, there's this lovely picture here. We have this on the wall at the Institute of Astronomy. It's two different star clusters of two very different colors. NGC 2014 in red at the right-hand side is a fairly classical emission nebula, hydrogen gas glowing in red, and a lot of new stars having been born in the center, a new star cluster emerging. And then in blue, NGC 2020, also discovered by that man, John Herschel again, the first one being John Dunlop. This one is a cloud of gas being lit up by the high energy radiation pouring away from a very massive star indeed, a Wolf-Rayet star, backed 9959. And these Wolf-Rayet stars are the biggest and most powerful class of stars, so powerful that they tend to blow away all their outer regions of hydrogen, leaving just a helium layer as the surface. So their spectrum is very much devoid of any hydrogen at all. And I think we can see the star in the center and the rings of material that have been blasted out from it. And those are now reflecting blue light because this star is super hot and emitting vast amounts of blue. Also inside the LMC, we have a supernova remnant where a star definitely exploded some time ago. And this is a Hubble Space Telescope image of DEM L190, which is very interesting because it contains what's called a soft gamma repeater. Again, you don't hear very much about these soft gamma repeaters. These are giving off bursts of gamma rays and X-rays from time to time, lower energy gamma rays, so soft gamma rays. And it's probably a magnetar, a highly magnetized massive neutron star spinning very rapidly indeed, creating very complex magnetic fields, which may account for the very wispy and filamentary structure in the resultant supernova remnant from the explosion that created this magnetar. So there are some fascinating objects in and around the large Magellanic Cloud. The small Magellanic Cloud, fairly similar but smaller, a little bit further away, 210,000 light years. It's several hundred million stars, but only 1/1000th of the number that make up the Milky Way, that is, and around about 7 billion solar masses. That's a lot less massive than the others. But there's a very interesting piece of history which I wanted to throw in here, which is that in 1908, Henrietta Swan Leavitt was using the stars of the Magellanic Cloud to do something quite remarkable. What she did was studied what were called cluster variables at the time and showed that these variable stars changed their brightness back and forth in a regular periodic way. So if you plotted a graph of the brightness over time, you got a characteristic shark's fin rise and fall at regular intervals. And what Henrietta was able to show was that the period of the variation was directly proportional to its apparent brightness. So that's very interesting. But what's more interesting is that when you're looking at the stars, the cluster variables in the small Magellanic Cloud, they're all 210,000 light years away, plus or minus a fairly small amount. So if they all are the same distance away, then their apparent brightness is a direct measure of how powerful they are relative to each other. And so what she discovered was that not only was the apparent magnitude directly related to the period, but the true power output must also be related to the period. And now we use this all the time as part of our cosmic distance ladder, because if you measure the period, you can know the true power of the star. And if you know the true power, you can compare that with its apparent brightness, wherever it happens to be. And using the standard candle rule, you can work out how far away it is. If it's twice as far away, you would receive a quarter as much light. 3 times as far away, 1/9 as much light. So the standard candle rule can be applied to these variables, which we now call Cepheid variables, after the first star of this type, Delta Cephei, that was discovered. So an amazing achievement and really, really helpful. There are lots of interesting things in and around the LMC as well as the SMC, and you can see some of them here. In the SMC, we've got NGC 376 imaged with the Hubble Space Telescope here, which has this curious sort of spike through the center of red stars there. It's about 8 light years across as a cluster, and it's beginning to dissipate. It's 28 million years old now, which is still fairly young for a cluster, but it seems to have spat out and lost about 90% of its original material. There's only 3,400 solar masses left, and the rest is spreading outwards and beginning to be absorbed into the rest of the SMC. Now, the two galaxies, the SMC and the LMC, have a bridge of gas and stars linking the two together. You can see it in this image here. This is an evidence, really, that they have not only interacted gravitationally with the Milky Way, but with each other in the past. And this tidal tail now stretches from one to the other. And there are new stars forming in the collapse of gas in the tidal tail, in this bridge of gas and stars. And one further thing is that we might actually be looking at 3 Magellanic Clouds. Matthewson et al. Proposed that this small Magellanic Cloud is actually split into 2 parts, and there is a smaller piece of it behind, 30,000 light years further away from us. And this was confirmed in 2023. The 2 parts really have distinct populations of stars with separate age functions and separate chemical composition ratios, and so does the gas that goes to make them up. And so these really are 2 separate clouds, 2 separate dwarf galaxies. So really we have the large Magellanic Cloud, the small Magellanic Cloud, and now the mini Magellanic Cloud as well. Sadly not directly visible to us easily because of the line of sight, but it's interesting that there is a 3rd member of the group. And it's amazing what you find when you're researching these topics. And I was looking into this one and I did not know about this, so I've learned something as well, and I hope you have too. So thanks very much for listening, and I'll just leave you with this fantastic picture showing the night sky over an observatory there. Thanks a lot, and we'll see you for another video another time.